Lab 3, Net Force from Star Data, the Mass of a Black Hole, submitted by Robert L. Stewart. Problem: a star is orbiting a black hole of unknown mass. The mass of the star is 1.98 times 10 to the 30 kilograms. And the black hole is assumed to be located at the origin. And the CSV file given the X and Y positions of the star every 86,400 seconds is provided. The net force on the system is due solely to the gravitational force of the black hole. We are to estimate the mass of the black hole. Here is a view of the CSV file provided in this lab with the X and Y positions at the beginning and the end of the orbit, along with the insertion of the time in both seconds and days to give a sense of scale. Here is a plot of the orbit of the star around the black hole. The black hole is indicated at the origin. Previously, we used Newton's second law to create a Python model to predict the motion of an object. But this time we have the motion of the object and need to determine the net force from the motion. We will use the position time data to determine the velocities, using the velocities and momentum to determine the change in velocity and momentum, and then determine delta P over delta T. This result is the observed effect caused by F net. We will resolve dp dt into components parallel and perpendicular to the initial velocities. The F net components follow. Here is a picture of the orbit. Picking the first three locations, R0, R1, and 2, we begin our analysis by specifying the initial velocity R1 minus R0 over delta t, and then we can calculate V1. We can take the difference between V1 and V0 to get delta V, and we can see that using the direction of the original velocity, we can determine the velocity change parallel and the velocity change perpendicular. We can do the same thing with the momentum vector. The momentum vectors will point in the same direction as the velocity vectors. We can therefore take the difference between the momentum vectors to get the change in momentum, and by dividing the change in momentum over the change in time, we get the F net. We can also see that we can get the parallel and the perpendicular components of these changes also. In the Python code, the visualization and graph setup are shown. The black hole is located at the origin at position 0, 0, 0. The system's property and data is specified: a star of mass 1.98 times 10 to the 30 kilograms, and the black hole at the origin. Delta T is 86,400 seconds, and the total time starts at 0. We read in the CSV file into a list XY, and then we create two new lists, X velocity and Y velocity, from this list to begin our computational loop, calculation loop. We calculate V initial and V final, P initial and P final, and of course delta V and delta P. From delta P, taking delta P and dividing it by delta T, we get dB dt, and that is set equal to F net by Newton's second law. Observations have now led to the cause. We determine, using the original direction of the initial velocity, P hat, the direction of the initial momentum, and determine dP dt parallel and dB dt perpendicular. And these are set equal to the F net parallel and F net perpendicular. We use vector subtraction to find dP dt perpendicular in this case. We then update the position of the star and show the force vectors calculated. And I wrote all this data to a CSV file for inspection, and I also printed out the last pair at the end so that we could see the mass of the black hole. Here you see screenshots of the star going around the black hole. The yellow arrow shows the net force, the blue arrow is the perpendicular component, and the black arrow is the parallel component. The net force always points towards the origin, allowing us to deduce that the F net is produced by the gravitational attraction of the black hole. It is interacting with our system, the star. We then calculate the mass of the black hole using Newton's law of gravitation, and the result is 1.99 times 10 to the 31 kilograms. The CSV file is imported into a spreadsheet, and we see that that result is consistent throughout the run of the Python code. What does it mean? Relate how FNet parallel and perpendicular are different from delta P over delta T and delta P over delta T parallel and perpendicular. Delta P over delta T and delta P delta T parallel and perpendicular are the observed effects caused by FNet parallel and perpendicular. The system's properties and motion allow the calculation of delta P over delta T and its parallel and perpendicular components. In this case, the gravitational attraction of the black hole located at the origin. What if the black hole whose mass you found was replaced by a different black hole, but the motion remained the same of the star around the black hole? Could you tell the difference? No, you could not. Since the system in its motion remains unchanged, the same mass will be determined using this analysis based on Newton's second law of motion. Therefore, it would not be possible to detect a different black hole was now located at that position. Thank you.